Hi all, my name is Guilherme Peccini. I would like to say that I'm very glad to give this presentation and the IWARA 2020 video conference. Okay. The talk I will present is entitled Study of Diffractive Gluon Jet Production in Electron Ion Collisions. I belong to the High Energy Physics Phenomenology Group, which is based at Federal University of Rio Grande do Sul, in the south of Brazil. I hope you all enjoy this talk. And for further details, I will indicate the paper that this talk is based on. So, the outline of this presentation. Here we are considering the diffractive jet production in electron-ion collisions in the regime where the diffractive mass is much larger than the photon virtuality. I will explain afterwards what are these variables. Okay. To do so, we apply the partial saturation framework since we are working at high energies, and we make predictions for future electron-ion machines such as EIC, LAGC, the HE LAGC, and the FCC EA. And the observable considered here that we will focus on is the differential cross-section as a function of the jet transverse momentum. And with this measure, we can extract the saturation scale. So this observable will enable us to extract the saturation scale from the experiment. This talk is based on a paper of mine and my colleague Lucas Morigi and Professor Magno Machado, whose title is Investigating the Diffractive Gluon Jet Production in Lepton-Ion Collision. It's available at arXiv with this code here. It will also be published shortly in Physical Review C. So what process are we considering? We're considering this process here. You can see on the diagram. Okay. Actually, we extended the analysis for electron-proton collisions to electron-nucleus collisions. Okay, so the electron interacts with a nucleus, and we have as a final state a diffractive jet and a gap, which is characteristic of diffractive processes. The observable considered here is the differential cross-section of this process here in terms of the gluon transverse momentum and the diffractive mass. Okay, the kinematical observables are the same as for diffractive deep inelastic scattering, where electron interacts with a proton. So here we have the Bjorken axe, the X Pomeron, which is the object exchanged in diffractive processes, and the beta. It's a variable which relates X with the X Pomeron. To describe the virtual photon, we will decompose it in its Fock states. First Fock state is the QQ bar, and the next Fock state is the QQ bar G. The interesting thing is that in the regime where the diffractive mass is much larger than the photon virtuality, that is, beta is much less than 1, just the QQ bar G component is important. And to the relevant diagrams for the scattering amplitude include the cases where the gluon is emitted before the interaction of the dipole with the nucleus, and the case where the gluon is emitted after the interaction between the dipole and the nucleus. So you have to consider these both diagrams here. So I will now show the the expression for the differential cross-section with this state here, QQ bar G, with the nucleus. This is the final expression for the differential cross-section in the red box. Of course, to verify the details and to check the details of the calculations, we quote the reference. We quote the reference of our paper. Therein you can see all the details and how we computed the expressions and so on. Here in these expressions, we have to calculate this variable here in the blue box, which depends on the scattering amplitudes. So how can we calculate these scattering amplitudes? But before doing that, we just have to say that this quantity here, why is this important? Because it rises as q square for small values of k, and falls as 1 over k square for large values of k. So it will indicate us where the saturation effects become important. So, as I said in the previous slide, we have to calculate the scattering amplitudes. How we can do that? With the S matrices, which are the scattering matrices in quantum mechanics. So this S is scattering amplitude for one dipole, and S2 scattering amplitude for two dipoles. Okay, because the gluon can be considering as one dipole within the BK equation. And the rho is a variable related to the wave function of wave functions of the virtual photon. Well, these the S matrices here are based on the GBW parametrization, okay, which considers the nucleus as a black disk. Okay, because of that we have the half-side functions here. So for the saturation scale, for the nuclear saturation scale, we adopt these ansatz here, which is based on the proton saturation scale. We have just to add the A, which is the number of nucleons in the nucleus, and the proton saturation scale is the GBW parametrization. Okay. For using these ansatz here, for example, in the case of gold nucleus, the gold saturation scale is approximately 2.8 the proton saturation scale, and for lead nuclei, the lead nucleus saturation scale is approximately 3 times the proton saturation scale. So we have increasing in the saturation scale, and this increases the saturation effects, and we can investigate the nonlinear regime of QCD. This is the main point here, and this is the main objective. We are increasing the saturation scale using nuclei instead of protons, and with that we increase the nonlinear effects of QCD. We also have to change the sigma 0. This is a parameter of the GBW parametrization. It's twice the proton area. For nuclei, we have twice the nucleus area. With the amplitudes based on the GBW parametrization, we can compose the final expression for the differential cross-section. Okay, this is it's a long expression actually, but it's easy to compute numerically. Okay, here to avoid the uncertainties relating to alpha S and sigma 0, we will define a new observable sigma scaled, okay, just to avoid the uncertainties related to alpha s and sigma 0, because this observable will not depend on these quantities. Before presenting the numerical results, so here you have a summary of the colliders and the beam energies, okay, for the IC, LHC, the high energy mode of LHC and FCC EA. The case of EIC, so we consider two configurations here: Q squared 1GV squared, MX squared 5GV squared, which is the black line here. Okay. And the other configuration is Q squared of 5GV squared and MX squared 25GV squared, which is the orange line here. Here in the red box we have the values of the differential cross sections for the first configuration, which is approximately 8 nanobarn per GV squared. And for the second configuration, we got 17 nanobarns per GV squared. Okay, these are examples. We are plotting the sigma scale in terms of the gluon transverse momentum. Since the hard scale in the problem is the gluon transverse momentum, the cross-section dominates at small values of a gluon transverse momentum because of the saturation effects. For the LHC, we plotted the Q squared times sigma scale in terms of a scaling variable, which is K over the saturation scale. Okay. We plotted this curve here for two values of mx squared, 50 and 200, and here we have two configurations. Okay, we have two configurations just to give you an example of the values of the saturation scale for lead targets, which is the case of the LHC. Okay. The interesting thing here is that this quantity here, the maximum value of the transverse momentum over the saturation scale, is approximately 1.5. We can clearly see here 1.5 at the peak of the curves. Okay, and this will be important to extract the saturation scale. Now we have the high energy mode of the LHC. We just have an increase in the center of mass energy. Okay, the high energy mode still remains the relation. Okay, K over saturation scale, approximately 1.5, as you can see here. Okay, so the next thing, it's not that equal in the case of the LHC. It's not that it's not the same thing, but it remains the same characteristics. Okay, the high energy LHC is just an increase in the center of mass energy. Now we have the most energetic project of the LHC, which is the first circular collider in electron nucleus mode. Here we plotted the differential cross-section in terms of the transverse momentum, the gluon transverse momentum, and the diffractive mass as well. We plotted this quantity against the diffractive mass for different values of the gluon transverse momentum. For two cases, the first being Q squared equals 10 GV squared, and the second case is 100 GV squared. Now we have a comparison among all the machines that we considered in this work. Okay, so we have here the first one, the black line is the EIC. Okay, the orange dashed line is the green line. The green dashed line is the LAGC. The next one is the high energy mode of the LAGC, in red, and the last one is the FCC, which is in blue. So here we have a comparison of the different machines. For this configuration here, Q squared of 10 GV squared and MX squared of 50 GV squared. We are plotting here K squared times sigma scaled in terms of K. Okay. So here is the interesting thing. Why you have a shift at the peak's position? It's explaining by the increasing of the nuclear saturation scale. Okay. Since the nuclear saturation scale depends on the Pomeroy X, and the Pomeroy X depends on the center of mass energy of the photon nucleus system. So here the FCCAA is the most energetic collider, and because of that the Pomeroy X is smaller than in the other cases, the other colliders. So we have the saturation scale is greater, which it leads to the fact that the position of the peak changes comparing to the other colliders. So what are the main conclusions of this study here? The maximum is related to the scale at which unitarity effects become important, the saturation scale. So this is very important, and we can clearly see that we can not only see where the saturation effects become important, but we can extract the saturation scale from the experiment. Remember that we have a simple relation which is K over Q squared is approximately 1.5 in all the colliders. So if we can measure the gluon transverse momentum, we can extract the saturation scale. It's very important. And to improve our work, we can consider different ansatz for the saturation scale. We have considered a very simple one. We could improve these ansatz considering other variables. Okay. And of course, we can implement more realistic expressions for the dipole nucleus amplitude. We consider the GBW parametrization, which is very simple and it takes into account that the proton or the nucleus is a black disk, which is very simple. One of the options would be to use the BK equation, the Balitsky-Kovshegov equation, which would be more realistic to describe the dipole nucleus amplitude. Okay. Before ending this presentation, I would like to say again that the details of the calculations and how we achieved the results and the plots could be clearly seen